All right, good morning, grade 10. So today we're going to cover linear quadratic systems. So like I said, this is the last lesson in unit 3. So I'm just going to go over the lesson as much as I can during this time. So in this lesson, pretty easy learning objectives. We're just going to learn how to solve a linear quadratic system. We'll talk about what that is and then solve more complex problems related to that. So what are the linear quadratic systems? So in grade 11, you might remember, sorry, in grade 10, you might remember that you learned about a system of linear equations, which is basically when you solve more than one linear equation simultaneously. And what you were doing with the linear system was you were trying to find out when they intersect. So if you recall in grade 9, actually, I think they did this back in grade 9. This was, equation 1. This was equation 2. You didn't call it functions then. You called it y1, y2. You were just simply trying to figure out when they were equal to each other. So you would set this up by using either substitution or elimination. Well, this is actually extremely similar. What we're doing is we're looking at where a line and a parabola will intersect with each other. So what you really want to do in this case is you want to figure out when the linear function is equal to the quadratic function. So this hopefully reminds you, as I mentioned already, of intersection of graphs, right? That's really what we're looking at, is the intersection of two graphs. So it's actually not too different of a concept compared to what you've done before. I hope you realize that, right? It's extremely similar. So there are a couple of possibilities for intersections. So a line, which obviously is represented by a linear equation, and a parabola, which is obviously represented by a quadratic equation, they can intersect in a couple ways, or not intersect actually in a couple ways, if you want to include all the possibilities. There could be no intersection, so you could have a parabola that opens up, and then maybe the line goes right underneath it and it just passes it, right? That's one possibility. You could have a parabola and it touches it at exactly one point, which is what we see over here. And it could also touch the parabola on the other side. Whoops, still not touching it like that, right? It just barely touches a parabola, right? This is actually something called a tangent, which you're going to learn about later on anyways. And then there's another possibility that there's two solutions. And for two solutions, what you would see is that straight line goes through the parabola twice, right? So you could have a parabola going like this, it touches twice. It could go like this, it touches twice right there. Or like I said, if it just goes straight through the vertex, straight through the vertex right there, and that's supposed to be a straight line, then that would be a case for just one solution. So there's a couple of different ways that you could have intersections there. So when you're considering all the different possibilities, what I hope you might realize is that this is actually not that different compared to considering how many possibilities there are for zeros of a quadratic function. So remember when we looked at how many possibilities there were for a quadratic function to have an x-intercept, and remember it was very similar, very similar to this, right? You could either have a parabola that opens up above the x-axis or opens down below the x-axis, which is kind of similar to what it's really similar to what we see here, right? We're just saying that this parabola could completely miss that line, like they would never intersect. Likewise, we could have one solution. It's very similar to this where it might hit the x-axis at the vertex, and it could also go open down like that, right? Which is extremely similar to how it's drawn here. It's actually not too different of a concept, right? And then, of course, the very last possibility that it touches twice. Well, this is very similar to what we saw with parabolas. It could touch the x-axis twice like that, or it could touch the x-axis twice like that, right? So very similar concept to what we looked at before. The only difference being that, instead of having the intersection of a quadratic and, a horizontal line, now it's a quadratic and just any diagonal line, right? It could be a diagonal line, horizontal, or we don't look at the vertical line. So just the horizontal or diagonal line, right? Does that hopefully make sense? Hopefully that makes it clear what we're really trying to find here. So this means that essentially because it's very similar to how we looked at the possibility or the possible number of roots for a quadratic function, it's actually going to be pretty much the exact same test that we're going to use. We're going to use the discriminant test. And if you recall, the discriminant test is when you check the value of b squared minus 4ac, and you only check the value of b squared minus 4ac because again, that is the value that is underneath the square root. So you don't have to check anything else. You just have to check what is under the square root, and that's it. So how do you find the intersections? Well, there's two ways to find the intersection of a line and a parabola. So graphically, you can check, you can look for the solution by drawing the graph of a parabola, and then you draw the line, and then you try to see where they intersect, if they even do that. But to be quite honest, I feel like that is a harder way to do it, and it's not always going to be that easy to graph. As we obviously we've seen that in order for you to graph a function, you either need to put it in. I feel like standard form is quite tricky because you need a table of values to go through that. You can put it in factored form, but you may not be able to factor it, or you could use a quadratic formula to find the zeros, and then you find another point on the graph, or you could complete the square in order to get it to in order to identify what the vertex is. So you have a couple options in terms of graphing, but I'm going to be honest, this isn't your best method, right? Because graphing a parabola is not always that efficient. So I would definitely say it's a better option if you do this algebraically. So algebraically, how you go about this is you actually make the two equations equal to each other. So you're essentially just ensuring that the f at x or the y variables are equal to each other. And then you move all the terms to one side, and then you solve by factoring or by using the quadratic formula. Okay. Now, remember, this is actually, I'm hoping when you see this, you'll realize how similar this is to substitution. It's actually not that different. I always kind of remind students because sometimes they look at this, they think it's like a totally new concept. There's actually a lot of overlap with what you've done before, right? The only difference is that when you bring it over to one side, you end up getting a slightly more complex quadratic, which means, and remember, quadratic equations you can't solve by isolating for x, right? It's not like you can get x by itself and then you solve, unless of course it's in vertex form. But normally, generally speaking, we can't really solve it that easily. What we need to do is we need to solve by factoring or by using the quadratic formula. But the good thing is we have two tools under our belt. So when you're solving algebraically for a line and a parabola, let's say that, and again, I'll give an example. Let's say that the equation of the line is f at x and the equation of the parabola is g at x. What we're going to do is we're simply going to take our line, which is f at x, and we're going to make this equal to our parabola, which is g at x. So we just make them equal to each other. And then what we're going to do next is move all the terms to one side. And then what ends up happening with this is that you end up with a quadratic equation. And then we know exactly how to deal with quadratic equations, right? And we actually saw that if you basically bring all the terms to one side, you can easily solve for the quadratic equation by either using factoring or by using the quadratic formula, okay? And specifically what we saw was the discriminant test. Sometimes you don't even want to know how many answers there are. Sometimes you just want to know, is there even an answer, right? It depends on the scenario, right? So only be one, if there is one, is going to be to the quadratic equation is going to be the x coordinate of the points of intersection. So it gives you the x coordinate of the point of intersections, but it doesn't give you the y coordinate. So how do you find the y coordinate? Well, pretty easy actually. To find the y coordinates of the point of intersection, you simply take your x coordinate that you found and you substitute it into function. Sorry, that's what I meant. So either the linear function or the quadratic one. And it doesn't make a difference which one you substitute it into, because remember, at that point, when you find your point of intersection, so if this is the parabola and this is the line, and let's say that they intersect at these points, x1, x2, it doesn't actually matter whether I sub it into the line or to the parabola, because we know that they're going to have the exact same y value, right? And again, I'm just drawing a really brief graph so you kind of see this. So I hope everyone can kind of see that, at that point of intersection right here, yes, they have the same x coordinates and the same y coordinates. So whatever the y, whichever, you can sub the x coordinate into either one of the two functions and you're going to get the exact same y coordinate. It shouldn't make a difference at all, right? So I hope you kind of can see that at that point when you're subbing in your x coordinates, you can sub it into either one of the two. So to determine the point of intersections, so let's do an example. Let's determine the point of intersections of the functions given. So we have a first we have a parabola there, which is negative 4x squared minus 2x plus 3, and 5x, and the line is going to be 5x plus 4. So to find the point of intersection, we're simply going to make both functions equal to each other. So we take function 1, which is a quadratic negative 4x squared minus 2x plus 3, and we're going to make it equal to 5x. Well, this looks a little complicated, but I do know how to solve this. All I need to really do is just bring all the terms to one side. Doesn't matter which side bring it to, but just bring it to one side. So I'm going to take away 5x here, and then I'm going to take away 4 there. And then I'm going to do it to this side, because whatever I do to the left, I do to the right. Now, I just want to make a point. Quite honestly, after doing the lesson, I realized that it probably was more efficient to bring the leading coefficient to this side to avoid having a negative leading coefficient. I tend not to like that, but I just you could solve it. You could either bring all terms to the left side or the right side. It shouldn't make a difference as long as you're being careful with this. That you should get the same answer anyways. So what I'm going to do now is, oops, and I forgot to put minus 5x. Forgot that there. So now what we're going to do is bring all the terms to one side. So again, with the 5x and the 5 and the negative, sorry, the 5x and the 4 on the right hand side are moved over to the left hand side. Plus 3 minus 5x minus 4. And of course, I'm going to join up the like terms. So this is going to give me negative 7x, and this is going to give me negative 1. So then I end up getting negative 4x squared minus 7x minus 1, and that's equal to 0. Now, I could definitely divide everything by negative 1, just so I switch all the signs. So this will all be, that's the benefit of moving it to the other side, is that we would have avoided that issue. But that's okay. We can still go about this question, right? Now, you always want to check, could you try solving this by factoring? You can take a quick glance and try to see if you can solve by factoring, but the answer is no. We won't be able to factor. So in my next step, if negative 4, negative 7, negative 1 are my A, B, and C coefficients respectively, what I'm going to do is I'm simply going to sub in negative 4 into A, negative 7 into B, and negative 1 into C. And then I end up getting this formula right here. So remember, this is going to be negative B, but remember, since it's the negative of negative 7, then I'm really just having a positive. I take negative 7 squared, which is 49, minus 4 times negative 4 times negative 1, divided by 2 times negative 4. And I go about these steps, and again, I'm not going to show all the work here. Negative 7 squared is 49. I would, like I said, be really careful with the signs here. Negative 4 times negative 4, sorry, negative 4 times negative 4 times negative 1, and negative 10. So you end up getting negative 16. So I'm going to write 49 minus 16, and then I'm going to divide everything by negative 8. So 49 minus 16 ends up giving us 33, and then we take 7 plus or minus square root of 33 over negative 8. And this ends up giving us 7 plus or minus approximately 5.74 divided by negative 8. And of course, that means that we have two solutions, and another solution in which we subtract the answer in the square root. And this ends up giving us 1.593 and negative 0.157. And there are our two x coordinates of the point of intersection. And then to find the y coordinates of the intersection, this isn't too bad. What you're going to do here is you're simply going to substitute the x coordinates that we just found into either one of the two functions. Now, my general preference is to sub it into the linear function. And the reason I say the linear function is better is because, going back to this, we have less operations, right? It boils down to which one is easier. Which one are you less likely to make an error with? I would say this one is less likely to have errors. So that's going to be a lot simpler to work with. So we're going to take our g at x, which is 5x plus 4. And I didn't show the work here, so I'll show it up here. So in the first one, 1.593, we're going to take 5 times 1.593. And then we're going to subtract off, sorry, we're going to add the 4. Or I think I wrote that wrong, hold on. Yeah, 5x plus 4, okay, there we go. I feel like I did something wrong here, sorry. Sorry, just checking myself the solution here. I think something was wrong because I don't think that would make sense. We would end up with a positive, which wouldn't make sense as the answer there. Sorry, I just want to check this here. Bear with me. Yeah, I end up getting a negative there. So I think something is, I feel like I did something wrong here. Oh, yes, I did. This should definitely be a negative right there, and I apologize for that. The one answer is negative 1.593, and the other answer is negative it's going to be negative 0.157. So I apologize for that. That's supposed to be a negative. Change that, please. And I'm glad I spotted that. So see, I make mistakes all the time, like I said. Please, and again, if you notice any mistakes, let me know, and I can definitely make that change. I really appreciate it. It's very easy to make a mistake with this. So I just don't want to Yeah, if you spot anything, so that sign should be negative. That was totally my bad there. So it's always a good idea to also. So here we have 5 times 1.593. Let me just write this down. Let me do the math, and then we add the 4, and that's going to give you negative 3.9565. So I just forgot to put the negative there. And then of course I'm going to go through the same steps here. I'm going to take 5 and I'm going to multiply by negative 1.593. And then I'm going to add the 4, and that should give me approximately this answer right here. And again, you can just double check yourself that that is actually correct. But that does seem to make sense. Oops, 0.50. You know what? I'm making tons of mistakes today. Just ignore what I'm doing right now. I'm basically just substituting in the X values right here. So I hope you understand what I'm doing there. Oh yeah, I'm totally making tons of mistakes today. I apologize for that, guys. So let me just fix that up. What I meant to write was that I'm subbing in negative 0.157. And again, let me just do the math here. Let me just make sure I'm on the right track here. I will grab a calculator, make sure I'm not making any mistakes. 1. Yes, I end up getting 3.215, and that's correct. Okay, so all we do there is just simply take our x coordinates and we sub it into our function. It normally doesn't take that long, I promise. Just today I was making a lot of errors there, okay? So what I want to show you is graphically what this looks like. And just before that, I'm going to change this on the slide just before I forget, because if not, I will totally forget to do that. And this should be negative right there. Perfect. Okay, so we can actually see that the answers graphically also make sense. So we can use technology to confirm that our answer is correct. I want to make something really clear. I know Ms. Bound, I mentioned this, but obviously cohort B was not in class yesterday. That when you try to find out, when you try to solve different problems, you can possibly use Desmos to confirm your answers. It's basically like a calculator, right? It's a great way to check if you're kind of on the right track or not. But just so you're clear, this is not going to give you if it's of your Desmos graphs, doesn't count for anything. You won't get any, you won't even get part marks, right? Because really that doesn't really help us much. All that's really showing us is, okay, you know how to use Desmos to check your answer. That would be like taking a screenshot of your calculator, right? It would be extremely similar to that. It doesn't make any sense. They're not the be all end all, right? It doesn't give us the full solution. So please don't assume that you can just take a screenshot of your Desmos graph and you're done. That's not really how it works, right? You have to be able to interpret it. You have to still analyze the graph itself and understand that you're not just done when you do that, right? So hopefully that makes it more clear. So we can see here that the parabola, let's look at the parabola in red, and actually you can see the labels here. Let's look at the parabola in red and blue. So we can see here that they intersect at this point right here and at this point right here. So notice that the x coordinates actually match up. So if we actually kind of go all the way down and we look at the x coordinates there, if we look at the x coordinates on the x-axis, you'll notice that those are the x coordinates of the quadratic function when we move everything to one side. So if the resulting quadratic function that we get when we move everything to one side ends up being negative 4x squared minus 7x minus 1. So notice that that is actually the zeros of that quadratic function that we get when we move everything to one side is the exact same as the x line. So what we kind of noticed is that, when we set them up and made them equal to each other, we actually ended up with this resulting quadratic equation. We already saw that. And this is basically just trying to solve for the zeros of the function. I actually don't want to call it f at x, I'll call it something else, h at x, which is negative 4x squared minus 7x minus 1. So what I noticed is that really what we're trying to do is just find the zeros of this quadratic function there. So let's do a bit of a tougher example. I feel like these are always going to be the tough ones. People tend to struggle with this one the most. So what we're going to do is we have a bit of a problem where there's going to be kind of you're going to end up getting like almost two problems in one, right? So in this question, any number, okay? So normally we'll specify that. We'll say k is any number, just a general number, and we want to find out what value of k needs to be so that this function, it's a linear function, 3x plus k, so that this function right here intersects with the other function, 2x squared plus 5x plus 3, g at x, just to avoid any confusion. But that's okay. It doesn't really change the question too much. We're just trying to figure out what the value of k needs to be so that so this line right here intersects with this quadratic function exactly once. Let's keep that in mind, exactly once, one time. So what we need to do is we simply make the equations equal and make it directly equal to 2x squared minus 5x plus 3. Notice that this is actually really similar to what you've seen, even if you're wondering, like, is there questions similar to this from before? If you look at test 1, you had a question that was extremely similar to this value of x, so that f at 2x is equal to g at 2x is the exact same thing. The only difference is that we're subbing in 2x, but here you're just making the two equations equal to each other. So what you end up with is 3x plus k is equal to 2x. To solve this, this equation, the intersection between the line and the quadratic, you have to bring everything to one side. So you're still going to do that. So I would suggest bring it over to the right-hand side. So I'm going to bring the 3x over, and I'm going to bring the k over. Now, this is where people get thrown off. They don't know how to treat that k, right? They kind of look at the k and they think, is that a new variable that we haven't considered? What is this k that we're looking at? Remember, k represents some number. It's literally some number. We don't know if it's going to be 5, 6, 7. What we know in this case is that k value, we need to figure out what it needs to be in order for that line, 3x plus k, to intersect with 2x squared plus 5x plus 3 exactly once. So you could do trial and error. You could try different numbers and see when you actually get a discriminant that's, I kind of told you, they end up getting, just one solution, but I feel like that's a very long way to do this, and that's not very efficient at all. So what you want to do is try to solve this more efficiently, right? So first thing, I'm going to bring everything to one side, and again, remember the k is really just a constant. It's some number, so we're going to treat it the same as the 3 here. If this had said kx, if there had been a little x attached to it, and if it had said kx squared, that means that it would be a quadratic term, right? So it depends on how it's written. If the k had been, so if we had kx squared, that would be, again, like I said, a quadratic term, which means that you would actually make it a like term with this one here. If it had just kx, it would be a like term with negative 5x. And if it had, but in this case, because it just has k by itself, we know we're going to join it with the 3, the constant there. So I'm going to erase all this. And then we end up seeing that we get, like I said already, we're going to subtract the 3x here. And then we subtract the k right here at the very end. So we join these two constants together. So this ends up giving us 2x squared minus 8x plus 3 minus k. Now, I mentioned this already. The 3 minus k, I'm going to treat it as if it's one coefficient, right? This is basically our a. This is our b, just so you're clear, the negative a together. And the 2 is the a, and then the 3 minus k is the c. So we see once again that we have a quadratic equation, but the only difference is that we have the extra variable k. So what we're going to do in this case, even though k seems, obviously, it's to be clear, k is not necessarily, we don't call it a variable in this case. We actually call it something, it has a bit of a special name. It's called similar to a variable. I don't want to go into too much detail about this, but parameter basically is just specifying that it's a value that they're very similar to variables. It can change, but in this case, it's not representing, one particular variable x that is independent. We're essentially just saying that this value is the one that could fluctuate, right? Like this number has to be so that we have one intersection, right? So again, for now, treat the k as if it's a number, because that's really what it is. I hope you understand that k just represents some number we don't know. And if we knew what that number was, again, I'm going to give an example here, something more concrete. Let's say that number was 10. What would you do? If this was actually to the other side, right? I hope everyone knows that. You would do the opposite operation. It's not that different, right? If you would subtract the 10, if it was a 10, or if it was negative 10 and you added a 10, well, it's the same idea here. All I'm asking you to do is simply do the opposite of adding a k, subtract the k on both sides. And so what we realize is that the 3 minus k together ends up with our a coefficient, our b coefficient, and our c coefficient. So looking at that, this hopefully looks familiar. You can say, can I try to solve this? Yeah, we can definitely, and we could try to use a quadratic formula to find the solution. But I'm going to tell you right now, it's not really going to work well, right? And remember, what did the question actually ask you to do? Did it ask you to be interested in what is the value for k for which these two graphs would intersect exactly once? So if they only care about how many times they intersect, then we just use the discriminant. We don't have to use a quadratic formula. So we're going to use the discriminant test to check when is b squared minus 4ac equal to 0. That is our goal. Our goal is to figure out when is the discriminant equal to 0. So we take our discriminant, b squared minus 4c, and we simply replace the b2, negative 8, and 3 minus k respectively. So we end up getting negative 8 squared minus 4 times 2 times 3 minus k. And then what we notice here is that we end up getting, obviously using order operation 64,
minus 4 times 2, which is 8, and then multiply by 3 minus k. This ends up giving us 64 minus negative 8 times 3. And again, I'm going to expand this out with the sign. Be really careful with that, right? There's a negative there. So we expand it out. We end up getting 64 minus, and I'm going to show the work here. I forgot to show it there. 64 minus 24. And then, of course, negative 8 times negative k gives us positive 8k. And then my next step here, I get 64. Oops, actually, I might as well just solve it. So again, all I had to do right here, I had a little in-between step. I had to distribute the negative 8 to both terms inside the bracket plus 8k, because of course a negative times a negative is a positive. And then I end up getting 40 plus 8k. So this is my discriminant right here. So now we know that if it has exactly one solution, then you want your discriminant to be equal to 0. So all we need to do right now is simply set the determinant equal to 0. So here's my determinant, 40 plus 8k. I'm going to set that equal to 0, and I'm going to solve for k. So when I do that, I know I need to bring everything to one side. So take away 40 on both sides. This ends up giving me 40 is equal to negative 8. Sorry, actually, I decided to bring it to the other side. I'm not sure why, but that's okay. You can go about it a different way. I was going to say, I think it's easier to isolate for 8k, but who knows? I'm not sure why I did it that way, to be quite honest, but that's okay. Let's just go with what we have here. It's going to give us the same answer anyways. We're going to divide by negative 8 on both sides. And then we end up getting k is equal to negative 5. And that means our k value is equal to negative 5 there. With these questions, I feel like the best way to go about this is just to practice, right? You need to do it a couple more times for you to kind of understand this. And last thing I want to mention, this is from yesterday's lesson. In general, with these questions where you have to deal with the k, just remember that what you're really trying to do, because this question, to be honest with you, is still a little bit easier. I could make this more complicated by saying, when could there be two solutions, right? So if the question has said, when could there be two solutions, what you would really be doing is trying to figure out when 40 minus 8k is greater than or equal to 0. So you could solve this, and again, we haven't learned how to solve inequalities, but I mentioned this yesterday. How you solve this without doing the algebraic breakaway is doing a graph, right? Do we know what 40 minus plus 8k is equal to? Well, we can graph it out. We can see graphically what it looks like and what this roughly looks like. And it doesn't even have to be a perfect graph, just yes, a straight line that has a y-intercept of 40 and it has a positive slope of 8, right? So that means that we're increasing by 8 each time. So roughly speaking, it's going to look something like this. It's going to go up by 8 each time. So this is 1, and it's going to be a straight diagonal line, kind of like this. Something like that, right? Now, if you're wondering, well, where's the x-axis, right? Sorry, where's the x-intercept, right? Because that's probably what you want to know. You want to know your other key point. Well, the x-intercept, luckily, we can actually find it relatively easy. To find the x-intercept, we simply make 40 plus 8k equal to 0. And then we can solve this by bringing the 40 over. So we end up getting 8k is equal to negative 40. And actually, we already solved it right here. That means that the x-intercept is going to be negative 5. So that means that it's going to hit the x-axis at negative 5. So if the question had asked you, when are you going to have exactly two solutions? Well, I'm going to have exactly two solutions when k is greater than negative 5. And I'm going to have no solutions when k is less than negative 5. So you simply just look at that's really what we're looking at, right? So when the discriminant is equal to 0, you're just trying to figure out when does that discriminant hit the x-axis. And that's all you're looking at. You're looking at the x-intercepts. When you're trying to find out when there's two solutions, you're looking at when the function, whether it's a parabola or a line, is above the x-axis. And then when you are trying to figure out if there's no solutions, you're trying to find out when the discriminant is less than 0. And that's graphically what that means is you're trying to find out when is the graph below the x-axis. So I hope that kind of makes it a bit more clear, right? So practice with these questions. That's the best thing that I can say for this. It takes practice, right? All right, guys, I think that's everything for today. Good luck with the test. I hope it all goes well.